In this lecture, we're going to talk a little bit about an advanced communication technique in molecular communication that has received some attention in recent publications and experiments, and that is the use of molecular MIMO. Molecular MIMO is inspired by MIMO in wireless communications, and the idea is basically the same. So in wireless MIMO, you have multiple transmitting receivers, multiple receiving receivers, and the idea is that at the transmitter, you can apply a different signal to both transmitting antennas, and the receiving antennas receive a combination of the two signals. So what you can do is you can encode information in both the time and amplitude, as you would do with a single antenna, but also in terms of the space. So you can actually send different signals on both antennas so as to guide your signal appropriately to the different antennas. We can do something similar in MIMO, and how it would work here is you would have a molecular emitter, more than one molecular emitter at the transmitter. So again, these might be reservoirs, and we would emit molecules into a shared fluid medium. And then there would be, actually, let me draw those differently. There would be two different receivers, receiver volumes at the receiver end. And these might count the differing number of molecules within their volume. Actually, we're not actually going to do it this way. In terms of molecular MIMO, it's often assumed that the receivers are absorbing. So this will be a little bit unlike what we did with counting modulation previously, which is that they were non-absorbing. So for our purposes, you can set it up both ways, but for our purposes here, we will assume the receiver are absorbing, unlike our previous work on CSK. Now you can, if you want, set up a non-absorbing receiver for MIMO. It's just the results that I'm going to explain. The simplest results that are available are derived for absorbing receivers. Okay, so we're going to have to talk a little bit about spatial modulation in order to talk about this. So in molecular communication, we mentioned that there were many different types of modulation that you could use, and one of them was spatial modulation. So if you imagine multiple receivers, even in one dimension, imagine multiple transmitters and receivers separated by a very large distance. So in other words, you would have a transmitter over here releasing molecules into the environment, and a receiver volume, and a different one, so a long distance away, a different one potentially releasing molecules into the environment, and a receiver volume over here. You could potentially, you could send a symbol by selecting which receiver to use. That's the idea of spatial modulation. I mean, that's a very simple way of describing any kind of spatial modulation, which is to say that if I want to send a 0, maybe I'll send a molecule from this emitter, and presumably it will then arrive at this receiver. If I want to send a 1, perhaps I will release a molecule from this emitter and it will be received at this receiver. And if there is a sufficiently long distance here, there is practically no chance that these will cross. That, in other words, that something released from here will arrive there, or vice versa. So that is the basic idea. We generally do not see spatial modulation in isolation. Instead, it's combined with other forms of modulation. But first, I'm going to think a little bit about a communication system, molecular communication, in higher dimensions. So far, we have restricted ourselves to 1D systems. And this is done for convenience and because they are easy to analyze. A 1D, I would like to point out, a 1D system can be mapped to a 3D system as follows. So assume that the medium, let's define, sorry, let me back up. Define the x direction as the original 1D axis of propagation. So as long as the system looks identical in the y and z directions, the system is identical. The 3D system is identical to the 1D system. So this is just a way of thinking about how to map from the 1D systems that we've talked about to 3D systems, and then we can generalize. So what I mean by this is originally we had this. So there's your transmitter at the origin. And then depending on whether we had an absorbing or a non-absorbing receiver, in any case, its boundary was here, the first boundary, Rx boundary. So in 3 dimensions, what does this look like? What this looks like is that this would be the x direction, and then you have 2 more directions, the y and z directions. So basically everything has to look exactly the same in y and z. In other words, if I take any coordinate in y or in z, the boundary is still distance d away. In other words, the boundary now becomes is a plane in y and z. So if I try to draw this in 3 dimensions, I might not succeed, but here would be the origin. So the transmitter is still here, and the receiver will still be located D away, but it has to be located D away in every dimension. So in other words, this will be an infinite plane. Located D away from the origin at yz equals 0. So in other words, anywhere I go here in y and z, if I stay at x equals 0, then the receiver is still D away. So the reason why this works because the Brownian motion is independent in each dimension. So in other words, the Brownian motion in the y and the z direction is independent of the x direction. So I can extract the x component of the motion, and everything in y and z is the same. Okay, so that's just a way to visualize how things work in higher dimensions. So in other words, our results that we originally applied to 1 dimension still work in 3 dimensions. But now we're going to do something a little different. We're going to generalize this. So we have to generalize this to spatial modulation schemes. So now what I'm going to do is I'm going to have more than 1 transmitter. They're again going to be point transmitters. I'm going to have 2 just as an example. You can have as many as you want. And then the receiver is going to be a sphere. So again, molecules are released at the transmitter. They propagate, and they can end up in either spherical volume over here. The distance we have here to the center of the sphere is still going to be d. The radius of the sphere will be r. They're going to be the same. So each sphere is going to have radius r. Just for convenience, this distance will again, excuse me, that's not right. The distance isn't to the center, it's to the edge. Oops. And there will be a distance of h between the spherical boundaries. Okay, so in this circumstance, it has been shown, we will not show, but for a single absorbing receiver, 3D absorbing spherical receiver, the average number of arriving molecules at time t is given by, and again, I will draw the environment here. So that is D, that is R, So the average number of arriving molecules, I'm going to give this the function f of t as a function of parameters r, d, and diffusion coefficient capital D. So again, that's the diffusion coefficient, as usual. This is given by, we're not going to derive this. This has been derived. I'll give you a reference later. Actually, I will put the reference in these notes once I upload them. R over R plus D, ERF C, D over root 4 dt. Okay, so now we know basically this is in some sense the impulse response of the system. If you release molecules from here at time t, or excuse me, from here at time 0, the number that you will receive is given by this, R over R plus D, or C, D over 4 dt. All right, so that lets us set up a hybrid modulation scheme. We haven't talked formally about hybrid modulation schemes just yet, but let's talk about hybrid modulation schemes. And MIMO. So remember, if we had pure spatial modulation, then we would only be encoding information in space. But now we're going to encode information in space, amplitude, and time. So what we're going to end up with is a sequence of symbols for each transmit antenna. These will be in discrete time. With symbol interval TS. Before I used TS as the sample time, but it's consistent. The sample time can also be the symbol time if you send a second symbol immediately afterwards. So the kind of setup we're looking at here, again, we have our, just for example, we have 2 transmitters, 2 receivers. They're both spherical. And what we're going to do is we're going to input sequences X1 and X2. And X1 and X2 will consist of numbers of released molecules. So in other words, let's say, for example, X1 is equal to 0, 1, 1, 0, 1. What that would mean is that in the first symbol interval, we send no molecules. At the beginning of the second one, we send 1. At the beginning of the third one, we send 1. At the beginning of the fourth one, we send 0. At the beginning of the fifth one, we send 1. And again, we could potentially have a different sequence at the second transmitter. So here it's 0 and 1, 1 and 0, and so on, and they both release a molecule in the 5th time interval. So something like that. So you can see how this would set up a hybrid modulation scheme because I am sending information in time and with amplitude, but also in space because these are different. So much like in conventional MIMO systems, I'm going to define a channel response and I'm going to define it Sij of k. And this is defined as the probability that a molecule released from transmitter I is received by receiver J in the kth symbol interval. In the previous lecture, we noted that probabilities could also represent impulse responses if the number of molecules was sufficiently large. So we dealt with that in the previous class. So you can think of this, it's convenient to think of it as a probability for analytical purposes. In other words, in order to derive it, it's appropriate to think of it as a probability. But for analyzing MIMO communication systems, you can also think of this as the impulse response. So this is also the impulse response if the number of molecules is large. So this lets us set up our MIMO matrices. What we'll end up with is, well, if you think about it for a moment, if I consider the number of molecules arriving at antenna 1, or the expected number of molecules arriving at antenna 1, I'll just, instead of writing expected value, I'll just write the number and just make the expected value implicit. That will be the number, at time k. That will be the number transmitted from antenna 1 at time k times S11, departing from 1, arriving at 1 at time k, plus the number departing from time 2 at time k, S departing 2, arriving at 1, okay, plus a noise term. So the noise will allow us to convert from, we talked about noise in the last lecture. We talked about counting noise as a data-dependent Gaussian noise, and that's basically what this will end up being. Similarly, y2 of k is x1 of k, s21 of k, plus x2 of k, s22 of k, plus z2. Now, you'll notice that we ignore ISI, and I'm going to ignore ISI for the purposes of this lecture simply because we have to simplify things in order to fit in the time allowed. So to be clear, we're going to ignore ISI. ISI is actually a huge issue for these systems. So my ignoring ISI is not to suggest that it's not important. It's just that we don't have time to talk about it. So we end up with the matrix equation y1, y2. I'm going to eliminate the dependence on k, just make that implicit. This will be S11, S12. Sorry, correction. Let me just make sure I'm getting this right. This should be S21, S12, S22 times X1, X2 plus my noise. So again, the noise term is data dependent. Counting noise. It could also be, there could also be other sources of noise. All right, so if we know all of these quantities, then the simplest way to detect the signal is simply zero force. So actually, there's a whole bunch of ways in which you can possibly detect, a signal, a MIMO signal. But just for simplicity and in the interest of time, let's just talk about zero forcing. So what we're going to do, let me just write this. There are many possible detectors for MIMO systems. But here, we will focus on zero forcing. And basically what happens there is the following. So again, redrawing my equation. I can define my terms here. So this will be the vector y equals the matrix, I'm going to call that H, the vector x plus the vector z. So in zero forcing, we invert H. So in other words, we multiply on the left by H inverse. H will generally be invertible because, at least in this scheme, the receivers, your cross receivers will be further away than your true receivers. So these elements will be larger than those. So this matrix should be invertible. So it'll be H, sorry, just a sec. H inverse y is equal to x plus H inverse z. So this, it's the linear combination of Gaussian noises. So this will still be Gaussian. We now have our signal without cross terms. So this is just the pure signal. And so basically this has been accomplished by linear operations. It's actually not the best way to do this. And I've also not described anything about how to design the signal for MIMO, but this will work quite well. Just want to finish this part of the lecture with some concepts. One is for the analysis of molecular MIMO is exceedingly complex. So basically what I just showed you were some ways to analogize it to wireless MIMO, but molecular MIMO is quite complex. There are many issues that have to be dealt with. So for example, one is that the molecule counts at the receivers are not independent. That's kind of a big one. If you think about how that works, if a molecule is counted in here, then it's not over there. So in other words, the counting noise is actually dependent. In a way that is actually kind of annoying and hard to deal with. ISI is a major consideration. So we skated through it. We didn't really talk about it at all. But techniques that you can use to mitigate ISI, you can modify the transmitter waveform to minimize ISI, like you can pre-code, something like that. You can do molecular pre-coding. You can also adjust the threshold at the receiver. But this is, in fact, dealing with ISI is actually the biggest factor in designing the receiver. It turns out to be a very complex problem because of the very long tails. And it's not feasible to wait for ISI to die out. So that gives you a very brief and high-level introduction to the idea of molecular MIMO, but it should be clear that there's plenty to do, and there's in fact plenty of research activity to do. Nonetheless, the gains, if you read the papers, are quite impressive, and it's certain that that molecular MIMO is a useful technique for increasing the information rate of MIMO systems, or excuse me, of molecular communication systems. So I would encourage you to check out that literature. I'm going to put right here, as I mentioned a second ago, in my notes, I'm going to put a reference to the paper that I based part of this lecture on. It'll give you far more information than I've given you here.